Hey everyone, in this video I'm going to be talking about how to derive the normal shock relations. The overall goal is to find out how Mach number, velocity, density, pressure, and temperature change across a normal shock. And a normal shock is one that is perpendicular to the flow. So if I have flow coming in from this way, I have a normal shock like this, and these properties change across this normal shock. And so, assuming that we have a calorically perfect gas, we can get these closed form solutions for the Mach number, velocity ratio, density ratio, pressure ratio, and temperature ratio across normal shock as only functions of gamma, which is the specific heat ratio, Cp over Cv, and the upstream Mach number, M1. So here's the process that we're going to use to solve for these normal shock relations. The first is to assume a CPG, as mentioned on the previous whiteboard. We're going to assume that the process is very nearly adiabatic, and we're going to use the 1D mass, momentum, and energy conservation equations. From those conservation equations, we can obtain expressions relating U1, A1, U2, and A2, where U is the flow velocity and A is the local speed of sound. Then we're going to obtain the Prandtl relation, and then we're going to use what we know to get the desired expressions. We're going to start with the mass, momentum, and energy conservation equations listed here. All of these are 1D. I have a video for the derivation of each of these equations that I'll post here in the video description. You note that the adiabatic assumption comes into play in the energy equation. So we need an expression relating U1, A1, U2, and A2, and we're going to get the first expression by using the momentum and the mass equation. So first we're going to divide momentum by mass. We're going to divide this equation by this equation here, and you can see that if we take P1 divided by rho 1 U1, we get P1 over rho 1 U1, and then this term here divided by rho 1 U1, we're just left with, since there's a squared here, we're left with just U1. Same for the right hand side here, dividing this by this. Now we're going to use the definition of the speed of sound. I have a video on this as well. And we have A is equal to, so A is the local speed of sound, is equal to the square root of gamma P over rho. And so if we just square both sides, we get A squared is equal to gamma P over rho. And if we rearrange this by just dividing both sides by gamma, we get P over rho is equal to A squared over gamma, which means that we can plug this in, this P over rho. You'll notice that there's a P over rho on both sides of this equation. We can plug that expression into here, and you'll note that then we only have A squared, or A, and U's in this equation. So plugging in that expression from the previous whiteboard into that combined mass momentum equation, we get A1 squared over gamma U1 plus U1 is equal to A2 squared over gamma U2 plus U2. And this is the combined mass momentum equation using the definition of the speed of sound for a perfect gas. Now we're going to move on to the energy equation, which I've rewritten here. We're going to use the fact that the enthalpy is equal to CPT, where for a calorically perfect gas, CP is equal to a constant, so CP1 is equal to CP2. And so if we plug that in here, we get CPT1 plus 1/2 U1 squared is equal to CP2 plus 1/2 U2 squared. Now we're going to use that CP is equal to gamma R over gamma minus 1, and I have a video on all this, and plug that in for the CPs here, and we end up with gamma RT1 over gamma minus 1 plus this is equal to gamma RT2 over gamma minus 1 plus this. Now we're going to use the definition of the speed of sound, same as was on the last whiteboard, just in a different form here where we have it in terms of R and T instead of P and rho. So we have A is equal to the square root of gamma RT, so A squared after squaring both sides is equal to gamma RT, and you'll note that that's what's on the numerator here in this first term. So we can plug in A squared for that. So we have A1 squared over gamma minus 1 plus 1/2 U1 squared is equal to A2 squared over gamma minus 1 plus 1/2 U2 squared. And you'll note that now we have two equations, these two boxed equations, and there are two unknowns. It may look like there's four unknowns, but what we actually know in these questions is we know the upstream values. For example, if you have a supersonic jet flying at Mach 3, then you know the upstream values. You know that the upstream value is that you're flying at Mach 3, for example. So what the unknowns are in these two equations are the downstream states, and that's the state 2, so A2 and U2, similarly A2 and U2 here. Now before we can move on, we have to note that the energy equation is defined by a constant. So I'm going to go back to the original definition of the 1D energy equation shown here, and if you note that the stagnation enthalpy is defined as H naught, I have a video on this as well, H naught is defined as the static, so the stagnation enthalpy is defined as the static enthalpy plus 1/2 U squared, then you'll note that the energy equation here, the 1D energy equation that's adiabatic, we can rewrite that as H naught 1 is equal to H naught 2 is equal to a constant. And so that's like saying A is equal to B is equal to C is equal to D is equal to some number that doesn't change in our flow. And if there's some number that doesn't change, that is a constant. So now I'm going back to the energy equation that we derived a couple whiteboards ago, and we know that now it is equal to a constant. So in the same way that a stagnation condition is a convenient reference state where we slow down the flow to zero velocity, we can use a different convenient reference state to find out this constant, and that's where the flow Mach number is equal to 1. So this is the sonic condition, and we're going to denote this sonic condition by the star superscript here. So when the Mach number is 1, the speed of sound is equal to A star. So we're defining this star state here. And so by the definition of the Mach number, which is now 1, as the local speed or the local flow velocity over the local speed of sound, and since we know that A is A star, we've plugged that into here. That means means that since the Mach number is equal to 1 at this fictitious state, or at this reference state, U is equal to A star. And so we can plug that into one of these, either side, whichever one, and we end up getting this here. So I've rewritten just this term or this term here without the 1 or the 2 because it's a constant. So we have A squared over gamma minus 1 plus 1/2 U squared. And if I plug in for A, I plug in A star, and for U, I also plug in A star. Then we have A star squared over gamma minus 1 plus A star squared over 2. And now I can simplify down this expression. Technically this is fine, but it becomes more useful if we simplify this down. So I'm going to find a common denominator here. So in this case I need to multiply this term here by 2 over 2, which gives us 2A squared, A star squared over 2 gamma minus 1. And in this case here I need to multiply this by gamma minus 1 over gamma minus 1. So we get gamma minus 1 A star squared over 2 gamma minus 1. We have the common denominator here, so we can combine the top, and we end up getting, and I'm factoring out this because we have an A star squared in both of these terms here. I factor that out, so we end up having this 2 plus gamma minus 1, that's here, times A star squared over 2 times gamma minus 1. And this here, rewritten as just 2 plus gamma minus 1. And then we can simplify this down because 2 minus 1 is 1, so we have gamma plus 1 times A star squared over 2 times gamma minus 1, and this is equal to a constant. Now I've plugged in that constant that we found on the previous whiteboard into this equation here, which is still that energy equation. And I just want to step back for a second to show where we're going with this. If you recall the mass and momentum equation from a few whiteboards ago, it's this expression here. We have it as a function of A1 and U1 on the left-hand side, A2 and U2 on the right-hand side. From the energy equation, so from this equation up here, you can see that we can actually break this up into two equations because of these equal signs here. So we can say that this, the one term is equal to this constant, and the two term is equal to this constant, which means that we can solve for A1 as a function of, you can see there's a gamma, and then there's the U1 here, and then there's the A star. So we can solve for A1 as a function of gamma, U1, and A star. Similarly, we can solve for A2 as a function of gamma, U2, and A star. Now, if we plug these into the mass and momentum equation here, so I'm going to plug in A1 and A2 into the mass and momentum equation. That means that our left-hand side will be a function of gamma, U1, and A star. The right-hand side will be a function of gamma, U2, and A star. And what ends up happening is we can derive an expression for A star that's only a function of U1 and U2, and that's the Pratheesh relation. So that's where we're going with this whole analysis here. So you'll note in the momentum equation that the terms are A1 squared and A2 squared. So we'll solve for A1 squared and A2 squared here. So first we'll start with the A1 equation. And what I've done first is, so we're dealing with this term here and this term here. So I've subtracted this term from both sides first and then multiplied both sides by gamma minus 1. So we're left with A1 squared on the left-hand side. Then we have this term here, but we've multiplied by gamma minus 1. So I have this gamma minus 1 times this term here, which is given here. And then I've subtracted off that 1/2 U1 squared here, but we've also multiplied by gamma minus 1. So I have gamma minus 1 over 2 times U1 squared. And if we simplify this down, the gamma minus 1's cancel in here, and we end up with A1 squared is equal to gamma plus 1 over 2 A star squared minus gamma minus 1 over 2 U1 squared. And the exact same thing is done for the 2 term, and we end up with a similar expression, but this is in terms of U2 instead. So I've rewritten the mass momentum equation up here, and we're going to substitute in for the A1 squared and A2 squared solved for from the previous whiteboard from our energy equation into here and here. So rewriting this here, we have just the, in red, this is the normal mass momentum, and then I've just plugged in for A1 squared here from the energy and A2 squared here from the energy as well. And so we're just going to distribute these terms throughout. So I'm just going to distribute this to here and this to here, and then this to here and this to here. And we end up with this expression down here. And you can see that we have a U1 squared here and a U2, but in this case, in this term, we can end up having this canceling with this here, and then similarly over here we have a U2 squared in the numerator and a U2 in the denominator, so we have that canceling like that. And what you can note then is that we have two terms that both have U1, so we have a U1 in this term, U1 here, U2 this term, U2 here, so we can combine those terms. So I've left this first term the same, that's the same here. Now I have a plus sign even though this is a minus because I've flipped these two, so I have plus 1, that's where this 1 comes from, minus this gamma minus 1 over 2 gamma, that's this term here, both multiplied by U1, same exact thing on the right hand side for the U2 terms. I've just rewritten that statement from the previous whiteboard up on top here. What I'm going to do is I'm going to leave this here, take this, divide or subtract this from both sides to bring it to this side, and then I'm going to move this one to the other side over here. So on the left hand side you'll see we have this term here minus this term here. That's these two here. And then on the right hand side you'll note that both of these terms here are the same, which means that it's we can just take that term here and then we have the U2, we subtracted this from both sides, we have U2 minus U1, and that's what this is here. And so what we want is that we want to get a common common denominator on the left-hand side of the equation, that's this side. So we have 2 gamma u1 and we have 2 gamma u2. So in this term, we're going to multiply by 1, which we can write as u2 over u2. And then same thing on this side, we can multiply by 1, which is given as u1 over u1. That gives, on the left-hand side here, we have this gamma plus 1 a star squared u2 over this denominator, minus this term here, gamma plus 1 a star squared times u1 over that common denominator. And now you'll see that the only thing that's changing between these two terms is this u2 minus u1. So we have this factor here that's the same for both of them, and then we have u2 minus u1, and then if I bring down this term from before, we have this 1 plus gamma minus 1 over 2 gamma times u2 minus u1 here. And so from this equation here, you can see that we have on the left-hand side of u2 minus u1, right-hand side of u2 minus u1. So if we divide both sides by u2 minus u1, then they cancel each other out, and we're left with just this is equal to this here. So we have this expression here, and I'm just going to simplify down this term on the right-hand side really quick. This 1 we can just write as 2 gamma over 2 gamma, because we're trying to get this common denominator. So we have 2 gamma over 2 gamma minus gamma minus 1 over 2 gamma. And if we combine the numerator here, we have 2 gamma minus this gamma, and since it's a minus minus, we end up with a plus 1 here. We have the common denominator of 2 gamma, and 2 gamma minus gamma is just equal to gamma, so we end up with gamma plus 1 over 2 gamma. And if you now look at this equation here, you'll note that we have this gamma plus 1 over 2 gamma, gamma plus 1 over 2 gamma in this term. So if we separate that out, we have the gamma plus 1 over 2 gamma, and then we are left with a star squared over u1 u2. That's this here, and that's equal to the right-hand side, which we said was this gamma plus 1 over 2 gamma. So if we divide both sides by that term, we end up with the expression that a star squared over u1 u2 is equal to 1, and if we multiply both sides by u2, or u1 times u2, then we end up with a star squared is equal to u1 times u2, and this is that Prandtl relation. And now we can get moving with solving for the downstream Mach number. So here's the Prandtl relation up here, and if we rewrite this, we can get it in the form of a star over u1 is equal to u2 over a star. And if you recall the energy equation rewritten over here, this is that constant. Then if we divide this equation by u squared, we get this form over here. All I've done is divide the left-hand side by u squared, the right-hand side by u squared, and that 1/2 u squared, the u squared cancels out, so we just have plus 1/2. We can multiply both sides by 2 times gamma minus 1, so by this term, little term right here. So we end up with just the gamma plus 1 a star squared over u squared. And here we have the gamma minus 1 canceled out with this gamma minus 1, but we multiplied by that 2 as well. So we have 2 a squared over u squared. And then the 2 in this term cancels out, but we still have that gamma minus 1, so we have plus gamma minus 1. We're going to use the definition that the Mach number is equal to the local flow velocity over the local speed of sound. So if we rearrange this, we can get a squared over u squared is equal to 1 over m squared. And you can see that we can plug that into this term right here. So we have the same left-hand side here, but we have 2 times 1 over m squared, or 2 over m squared, plus gamma minus 1 here. We want a common denominator so we can combine these two terms, so I'll multiply this term by 1, which we can say is m squared over m squared, so we have the same 2 over m squared plus gamma minus 1 m squared over m squared. And if we combine these two terms, then we have 2 plus gamma minus 1 m squared, that's this numerator, all over m squared. And now to get this final form, we want to divide by gamma plus 1, because we want an expression for this a star squared over u squared, so we're going to divide both sides by gamma plus 1. After dividing both sides by gamma plus 1, we end up with the a star squared over u squared. We can just rewrite this as a star over u squared is equal to this form on the right-hand side, which is only a function of gamma and the Mach number. And now we can plug this into that rearranged Prandtl equation that I had on the previous whiteboard as well, where we had a star over u1 is equal to, so that's this term here, but we're going to take the square root of both sides. So I'm plugging in here, I'm taking this, plugging that in here, and now since we're talking about state 1, we can just plug in that the Mach number is the Mach number at 1. And then similarly for this term is equal to u2 over a star, so all we need to do is just flip these terms here, and that's why we have this gamma plus 1 m2 squared on the numerator, and then this term here in the denominator, again plugging in for state 2, so we have the Mach number at 2 there. Now we're going to square both sides and multiply by the denominator, so I'm squaring both of these sides because we have the radical on both sides. Get rid of that, and then I'm going to multiply this over to here, multiply this over to here, and we end up with this here, so we have the state 2 term here, state 1 term here, state 1 term, state 2 term here. And now what we're going to do is that the goal is to solve for the Mach number at state 2, so the downstream Mach number, and it's going to be a function of gamma and m1. So I'm going to distribute through this 2 to this term, and then this gamma minus 1 m2 squared to this term. So that's why we have this 2 times that term, plus gamma minus 1 times that term, and I'm pulling that m2 squared out here because the goal, again, is to solve for m2. Same over here, we're multiplying these two terms together, so we have this gamma plus 1 in both terms, so that's gamma plus 1 squared, m1 squared, and then we keep that m2 squared outside of this just because we're trying to solve for m2. So I've just rewritten that expression here at the top of the board, and now I'm going to distribute this term through this first term, so we have 4 plus 2 times gamma minus 1 m1 squared, and then I'm going to distribute this through both of these terms here, so we have 2 times gamma minus 1, that's this, and then we still have that m2 squared term here, plus the gamma minus 1, there's 2 of them, so we square it, times m1 squared, and then we still have that m2 squared here. And then on the right hand side, we have the same thing. Now you'll note that we have m2, 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 and over here there's just the m1. So I'm going to move all the m2 squared terms to the right hand side, so I'm going to subtract this from both sides, and I'm going to subtract this from both sides, and since these all have m2 squared, I'm going to group them all into the same term. So this stays the same, that's still on the left hand side. Now I have gamma plus 1 squared m1 squared, that's this term here. I subtracted off 2 times gamma minus 1 here, and we still have that m2 squared, but it's out here. And I also subtracted off this term here, that gamma minus 1 squared m1 squared, still have that m2 squared out here. Now you'll note in this term here, this entire term here, we have an m1 squared term and another m1 squared term. And so what we can do then is combine those two. So we have this gamma plus 1 squared that's here, minus gamma minus 1 squared that's here, times the m1 squared. We still have this minus 2 gamma minus 1 term here, and then we're still multiplying by m2 squared. So we can simplify down this. So if I take this, and I'm going to expand it out here, so we have this gamma plus 1 times gamma plus 1 minus gamma minus 1 times gamma minus 1. We distribute through here, so we get gamma squared plus 2 gamma plus 1, that's this. And then for this, we have gamma squared minus 2 gamma plus 1, so that's this here. And if we write this out again without these parentheses, we have the gamma squared plus 2 gamma plus 1, and we have minus gamma squared. The minus minus makes a plus 2 gamma, and then minus 1 here. And you'll note that the gamma squareds cancel out. The 1's cancel out, and we have 2 gamma plus 2 gamma is equal to 4 gamma, so we can plug that back in to here to simplify down this expression a little bit more. So now that we've plugged in that 4 gamma into the term preceding the m1 squared term, we have this expression here. The left-hand side was remained unchanged, and if we divide both sides by 4, then we end up getting this divided by 4, this term divided by 4 is 1 plus, and the 2 divided by 4 is gamma minus 1 over 2 m1 squared, and then in each term here we divide by 4, so we have just gamma m1 squared minus gamma minus 1 over 2 times m2 squared. And now we can solve for m2 finally, so we're actually solving for m2 squared. And all we have to do is then just divide this by this, and so we end up with m2 squared is equal to 1 plus gamma minus 1 over 2 m1 squared over gamma m1 squared minus gamma minus 1 over 2. This is the final form to solve for the downstream Mach number, knowing only the ratio-specific heats and the upstream Mach number. One important thing to note about this equation is, again, that it is m2 squared. So if you want to solve for the downstream Mach number, you will need to take the square root of the right-hand side here. The next thing that we can solve for is the ratio of the downstream velocity to the upstream velocity, or u2 over u1. So if we take the u2 over u1 and we multiply by u1 over u1, so that's just multiplying by 1, we end up with u2 times u1 over u1 squared. And you'll note that from the Prandtl relationship that u1 times u2 is equal to a star squared. So we just plug that in here. And then we can also say that this a star squared over u1 squared is just a star over u1 squared, and we already know what this term is. And so the final relationship for the u2 over u1 is equal to 2 plus gamma minus 1 m1 squared over gamma plus 1 m1 squared. Now we want to solve for the density ratio, rho 2 over rho 1, so we'll use mass conservation. From the first whiteboard, we have rho 1 u1 is equal to rho 2 u2, so rearranging this to solve for rho 2 over rho 1 gives u1 over u2. You'll note from the previous whiteboard that we have the expression for u2 over u1, so all we have to do is just flip that upside down, and we get the expression for rho 2 over rho 1 is equal to gamma plus 1 m1 squared over 2 plus gamma minus 1 m1 squared. Now we're going to solve for p2 over p1 using the momentum conservation equation that's repeated here. If I subtract p1 from both sides, I get p2 minus p1, and I'm also subtracting rho 2 u2 squared from both sides, so I get equals rho 1 u1 squared minus rho 2 u2 squared. And if we divide this equation by p1, then we end up getting p2 over p1 minus p1 over p1 is just 1. On the right hand side, I have 1 over p1 with the same thing here. We're going to use mass conservation as rho 1 u1 equal rho 2 u2. And you can see that we can replace this term here where we have rho 2 u2 squared. So if I take rho 2 u2 and I multiply by another u2 here, Then I have to multiply by another u2 on this side as well. And so we end up getting that rho 2 u2 squared, this term here, is just equal to rho 1 u1 u2, and that's what I have right here. And now what I want to do is I want to be able to take out this rho 1 u1 squared term, but on this side I only have rho 1 u1. So I'm going to multiply this right here by 1, which we can call u1 over u1, which is why we end up with u1 squared over u1 in this term here. And now you'll note that we have this rho 1 u1 term here, rho 1 u1 squared term here, and the rho 1 u1 squared term here that we can pull out of this parentheses here. So we end up having rho 1 u1 squared over p1. This is now a 1, and it was taken out of this term here, so we just have 1 minus u2 over u1. So we have that term rewritten up here, and we'll note that the speed of sound squared is equal to gamma p over rho. So if we divide both sides by gamma, we get p over rho is equal to a squared over gamma, but we need rho over p, so we'll just say that rho over p, we'll just flip it, and we get gamma over a squared, which we can plug in to this rho over p here. So we end up getting, after I also add 1 to both sides, we end up getting that the p2 over p1 is equal to 1 plus, and then here plugging in for rho over p, we get gamma times u1 squared, that's still here, over a squared, times this 1 minus u2 over u1. And if we note that u1 squared over a squared is equal to m1 squared, the Mach number squared at state 1, we end up getting 1 plus gamma times m1 squared times this 1 minus u2 over u1. You'll note that we have u2 over u1 from before, so we can just plug that term into here, and we end up with this expression here. Now, to simplify this term here, we want to get the common denominator of gamma plus 1 times m1 squared. So I just multiply this 1, we can just say, is the same as gamma plus 1 times m1 squared over gamma plus 1 times m1 squared. Now what I've done is I've just taken these two common denominators and combined those numerator terms here, and now I'm just going to distribute this term through by here and this term through by here, so we end up having gamma m1 squared, that's here, plus m1 squared, that's here, minus 2 minus gamma m1 squared, that's this term, minus a minus is plus, so we have plus m1 squared. And if you look at this term here, we have a gamma m1 squared minus gamma m1 squared, so those two will cancel each other out like this. And we end up with the expression that the p2 over p1 is equal to 1 plus gamma m1 squared, that's all the same, times we have m1 squared plus m1 squared, that's 2m1 squared, and then we have minus 2, so that's minus 2. Denominator stays the same. So we have this expression here. We'll note that we have a m1 squared in the numerator, m1 squared in the denominator, so those will cancel each other out. And we can take this 2 out, we can factor the 2 out from both of these here, out here, and we can end up with this final expression for the pressure ratio across a normal shock. P2 over P1 is equal to this 1 plus, and then we have the 2 factored out, so we have 2 gamma over gamma plus 1, that's this term, times m1 squared minus 1. Finally, we're going to solve for the temperature ratio T2 over T1 using the ideal gas law and P2 over P1 and rho 2 over rho 1 that we solved for before. So we have T2 over T1. I'm going to plug in for T2 from the ideal gas law, that is equal to P2 over rho 2R, and T1, since it's in the denominator, I'm just flipping these, so I have rho 1R over P1, and the R's will cancel out because they are the same, and we are left with P2 over P1, that's this term, rho 1 over rho 2, that's this term. Note that it's the opposites flipped of rho 2 over rho 1. So we end up with T2 over T1. We're just going to plug in for these two that we know, and we end up with this final expression that I will box. And this sums up all of the normal shock relations that we can derive in this video. Thanks for watching.